our final speaker, Professor Kerry Emanuel from MIT, Massachusetts Institute of Technology. And Kerry has been here, and actually last year, some of you have met him, and he is an atmospheric scientist, and at the moment is a professor in atmospheric scientist, and specialized in hurricane physics. And he's indeed actually the first one who look at this hurricane evolution in the context of climate change, long-term change. Because I remember this topic has been really debated even in Sweden, that do we see a change in the frequency, intensity, and many people argue that there's no change because in the US we have a long-term data. So I'm really keen to see what you say, Kerry, please.
Thank you. Okay. Right. Thank you. Well, thank you very much, Deliang. It's a great pleasure to be back in Göteborg with all of you. I always enjoy my time in Sweden. My talk is going to be a little bit different from the first two you heard because I'm going to focus in on one very influential phenomenon around the planet, which is tropical cyclones. And and their cousins, polar lows and Medicanes. The polar lows is a phenomenon that's occasionally experienced even here. And ask, how does climate change affect these? And my talk is going to be a little bit more focused on how science and how scientists go about evaluating these, because this is a kind of change that today cannot be evaluated directly from a climate model. We actually need to do something a little bit extra. Climate models aren't finely enough resolved to do this. And so I'd like to talk about how science really approaches these issues. So I'm going to talk about observations, including the ones that Deliang alluded to, and why we can't usually, when it comes to extreme events, it's very hard to actually see trends in observations, almost by definition. And the problem is that the events that do a lot of the damage, in the case of tropical cyclones, are events whose frequency is about once every 100 years. If it's more frequent than that, society is usually well adapted to it. But 100 years, we don't have 100 years of records. So we cannot wait. We cannot wait for the signal to unambiguously emerge in observations. And that means that if you are only interested in observations, you either have to trust people who do models in theory, or you have to start doing it yourself, all right? It's a dilemma. The assessment of risk is not the same thing as the detection of a signal. You see what I'm saying? I would argue that if somehow we only had 10 years of records of the weather, and yet we knew enough physics and had good enough models to be worried about the sorts of things that Sonia was just telling you about, we'd still be worried about it. All right? We can't wait always for the signal to be detected in observations. A little bit of technical background on why, for this particular phenomenon, we can't rely directly on climate models, but indirectly we must. Using physics to do something called downscaling tropical cyclone activity, and talk a little bit toward the end about Medicanes, tropical storm-like phenomena in the Mediterranean Sea, and polar lows, and then summarize. So are hurricanes changing? It's the first question people ask. I just want to show you one slide about the problems we have trying to detect this in observation. So this slide shows, according to the generally accepted historical records, the number of major hurricanes, category 3 and higher, going all the way back to 1851, but divided into two pieces. So these are North Atlantic hurricanes. Now remember, well, you may not know this, but only about 10% of the tropical cyclones on the planet occur in the Atlantic, even though they get 99% of the press, unfortunately. But we have the best records of this phenomena in the North Atlantic. Now, the two pieces are tropical cyclones that either pass through the Lesser Antilles, the eastern side of the Caribbean, or they made landfall in the continental United States, or both. And that's the blue curve you see there. The red curve are all the other storms. that didn't do that. Now, why have I divided it that way? Well, the Lesser Antilles were heavily inhabited over this whole period, and so was much of the coastal continental U.S. So the records are pretty good there, okay? The other storms are pretty good at the end of the record, but almost entirely missing at the beginning of the record, because you had to rely on the storm passing over a ship or some other island. And you can see two distinctly different trends. And atmospheric scientists don't believe that the physics warrants there being different trends in these two subsets. What you're seeing is a difference between well-sampled events through the whole period and poorly sampled events in the early part of the period for these storms that stayed out at sea. And so you look at that and you say, we really can't trust the record. I don't trust either of those trends. The record isn't up to it, all right? And yes, we can wait for another 100 years and see a trend. The fact that we can't do it with data doesn't mean that the underlying probabilities aren't changing. And so I'm a very strong proponent of bringing another way of knowing about nature into this problem, which is physics, okay? We cannot rely on actuarial approach using historical data to this whole problem. Not that alone. Here is a slide that's based on modern satellite observations over the entire globe. And it shows the trend in the number of tropical cyclones whose lifetime maximum wind exceeds the value you see on this axis. So basically, most of the storms we call hurricanes are above 80 knots. And if you take all of those storms, there's no detectable trend in their numbers. However, if you get to the stronger events, storms, say, greater than 120 knots, there's a pretty big increase in the number of those events in the record. And the shading in the background is a measure of the uncertainty in the trend. Right? So there's a big spread, and yet it's pretty clear the satellite data is showing us in the modern times, that is post-1980, a pretty big trend. And it was a trend that was predicted some decades before this. A little bit of theory, just very quickly. We can idealize, for the purposes of this, a tropical cyclone as a circularly symmetric phenomenon. This is kind of a cross-section through a storm showing essentially the upward component of velocity. So you have lots of air moving up the so-called eye wall of the storm and out. And we're going to take a little cross-section like that and blow it up into this. And we can talk about a thermodynamic cycle of a hurricane in terms of this diagram. So here's the center of the storm. This is height in kilometers. This is distance from the center. We're going to suppose that the circulation is steady, go from A to B to C to D, along with the air in this plane. And it turns out that these four legs, by the way, the colors in the background are a measure of the entropy of the system, an entropy of a combination of air, moisture, and water vapor, a quantity that's conserved unless you externally add heat or subtract heat from the system. When you go to A from B, it's an isothermal expansion. The temperature doesn't change, but the pressure drops. B to C is an adiabatic expansion. C to D is very nearly isothermal compression, and D to A is a adiabatic compression. It turns out to be the four legs of Carnot cycle. So those of you who've had some thermodynamics, it's the most efficient engine for converting heat energy, in this case to the mechanical energy of wind, that you can have. And nature somehow magically produces that in the case of a hurricane. From our knowledge of that, we can actually calculate an upper bound on the intensity of the storm. And here is for the current climate, a map of that upper bound in meters per second here. And we're picking off the peak value over an annual cycle. So you can see that according to these physics, you can have very intense storms, as you might expect in the tropics, and not at higher latitudes. But back in 1987, I wrote a paper which suggested that climate change, which wasn't on that many people's radars back then, would change this limit. And we can see now, after all these decades have passed, that it is changing. So this is from climate analysis data. It's not from a model, showing the trends in this thermodynamic bound on the intensity of hurricanes expressed in meters per second of wind speed per century. And they're very substantial trends in places that already have hurricanes and typhoons, like the western tropical Pacific, the Atlantic, and so forth, and a few downward trends where there aren't any tropical cyclones. And notice the big upward trend in the Mediterranean, right? When we look at climate model projections into the future, depending upon our assumptions about how much greenhouse gas will emit, we see a similar pattern of rather large trends here expressed as meters per second per decade, but you see upward trends in virtually all of the tropical cyclone-prone places. So theory tells us something, not everything, not this theory anyway, that the bound on how intense a hurricane could be theoretically should go up and is going up. And that led us to say a long time ago that we should see a higher frequency of the very intense hurricanes. And as I showed you a few slides back, there's indication in satellite data that we are seeing that. So I would summarize the inferences from very basic theory. This thermodynamic limit goes up with global warming. We've known that theoretically for 3 decades. Because of that, the incidence of hurricanes of high intensity should increase. Increases in potential intensity should be faster in the subtropics. I didn't say that a while back, but that is also something that comes out of the theory. And another very worrisome aspect of the physics of hurricanes is that a given storm should produce a lot more rain in a warmer climate. That's very elementary physics, about 7% increase at least, because of the increase in water vapor per 1 degree centigrade of warming. In point of fact, water kills far more people and does far more damage in tropical cyclones than wind. Everybody thinks of these as windstorms, and they are indeed windstorms, but what really kills people is water. So we're actually more worried about the water aspects of this problem than the wind. Let me use that as a launching point into the discussion of what a point of view I think we should take in respect to all extreme weather events that go along with climate change, and it's to put it in a risk framework. I think the field is beginning to do this. The previous speaker certainly alluded to this, but we haven't really sort of bought into this framework, which is an ancient one. It's just something that we haven't done in our community as much. What's the problem here? I'm going to show you a graph that a meteorologist might put of depicting the effect of climate change on tropical cyclones. So what are we looking at here? We're looking at probability or probability density here as a function of the intensity of hurricanes. So there's more intense here, less. But you'll notice that the bottom axis isn't expressed as the intensity of hurricanes. It's expressed as the damage those storms would do if they passed over. The way this chart has been created is to take many, many synthetic hurricanes and pass them over a particular set of property values in the United States. All right. So this measure of the hurricane isn't the wind speed in meters per second. It's the damage that hurricanes would do. It's another measure of the intensity of the storm. It's a social measure. All right. Now, the blue curve is for the current climate. Notice it's a log scale, by the way. That's very important here. So that's $1 million, that's $1 billion, and that's $1 trillion of damage. The blue is for the current climate, and the green is for a future climate. It's not important to talk about what future climate. I just want to use this graph to make a very serious point, probably the most important point I'm going to make in my half hour, all right? What do we see? That at the peak of the probability, where most of the storms are, that is, where there's the highest probability of encountering a storm of this particular damage potential, the frequency actually goes down in the future climate. According to this particular model, I should say. It actually goes down. And on the other hand, if you get out into the tail of the distribution, the frequency goes up, or the probability goes up. So a meteorologist, a journalist, a beginning economics student might say, well, the frequency of events goes down because the frequency is dominated by where the highest probability is, but the intensity of the events goes up. And it's something you'll read over and over and over again in newspapers. And it's completely misleading. All right? So now let's look at what a highly trained economist would do. He's going to take exactly the same data, all right, and portray it a little bit differently. What we're going to do is we're going to take the probability density and multiply it by the damage. Same data, we get these two curves. All right? Now, the total cost of hurricanes in both climates is the integral of the damage times the probability times the, over the probability times the log of the damage. So it's the area under these two curves. This is the current climate. This is the future climate. More than tripling of the damage. Okay? A totally different picture than the journalists and the meteorologists tell you. Oh, there's a trivial change in the probability of the tail. I've heard that statement by trained meteorologists many, many times. That trivial change in the tail is driving a tripling of the damage because you're in the tail. This is a risk. This is signal. Okay? This is risk. That's signal. If this is what's going to happen, this is what it's going to cost, not that. Okay? Do you all get that? It's an almost trivial point, and yet it's so important. And it's why we're here, right? It's why extreme events are so important and why we worry about them. But these are rare. The probability is small. 1 per century. We're going to detect that in historical data? Nope. Okay? So we have to turn to physics or other approaches. So why can't we use climate models? Well, climate models just don't have enough horizontal resolution to capture hurricanes. Sure, they generate something that looks a little bit like a hurricane. We just don't have enough computer power now, and are not likely to for a very long time, to resolve the eye, the inner core of a hurricane. So this is, again, a sort of a probability or frequency measure, but now back to a function of wind speed. This is the observed current distribution of storms. This is the arbitrary difference between a category and category 2 hurricane and a category 3 hurricane. This is from a state-of-the-art climate model, actually better than most in terms of resolution. All of the damage that's done, virtually all of the damage, is done by these guys to the right of this line. And the climate models don't simulate any of those. All right, so the climate models are simulating storms to a first approximation we don't care about. This is not an overall criticism of climate models. It's just they're not particularly good for this particular problem from limitations of computer power. 50 years from now, they might be. It's going to take a big increase to get us to that point. So global models don't simulate the destructive storm. So we're going to do something a little bit different. We're going to apply physics. And it's a long story that I don't have time to tell. But basically, we're going to take a very high resolution model that wasn't developed for climate purposes, but to help weather forecasters forecast real hurricanes. And we're going to embed it in, it's actually coupled ocean atmosphere model. We're going to embed it or drive it with the large-scale fields provided by a climate model or just a climate analysis data set. It doesn't have to be a model. It can be analyzed climate. And we're going to do that in a way that allows us to generate 100,000 synthetic storms. So we can produce from the same overall climate over a period of 20 or 30 years, not 100 storms, but as many as we like, 100,000 or so, and look at the statistics of these storms. It's really quite a fascinating endeavor, and yes, I'm skipping over a lot of the details. Here is an example of a mere 1,000 synthetic events generated from a climate analysis data set, not a climate model, although if I used a climate model, it would look pretty similar. These are the tracks of the synthetic storms. The colors indicate their wind speed. A lot of them intensify, and then as they move to higher latitudes, they weaken. If you've ever seen a chart of real hurricane tracks, you'll know how to compare the two. But of course, we have to subject these synthetic storms to very rigorous statistical tests to see how well they do in history. And we have done that over the years. But we can also get local with this. And this is where it gets interesting. I like to say that all climate change is local. And that mirrors a statement made by a long ago US senator who said all politics is local. That is, people respond to what they see around them much more than they respond to what hypothetically or actually might be happening somewhere else. A lot of people I know in the United States have changed their mind on climate because they got hit by something, a wildfire or a hurricane. It may not even be rational. In other words, a climate scientist might say, no, you can't do that. But they do change their minds. And so when we come to assess risk, usually we're doing it locally. Sometimes we're doing it globally. So this is a study we did for the city of Kyoto in Japan, where we generated a few thousand events that were filtered, or we only paid attention to those events, if you will, that passed over Kyoto in the southern part of Japan here. And the magenta curves are actual historical hurricanes. The other curves are the synthetic events. And the synthetic events have the same distribution of peak wind speeds as historical events. The blue is showing you the number of storms in history whose wind speeds have exceeded the value on this axis, and the red comes from the synthetic events. And this is just the annual cycle of storms. This happens to be for the North Atlantic, where the red is the synthetic events. The blue dots are from historical tracks. And it didn't come through on the projector, but there's some shading that shows you whether the historical events were at least hypothetically drawn from the same distribution as the synthetic events. Now, we can do this globally. So this is a study we did a few years ago where we downscaled 6 CMIT-5 models all over the globe at the end of the 20th century and then going off into the 21st century under this rather high-end emission scenario called 8.5. The solid lines show the mean across the 6 models of something called the power dissipation index, which is a crude measure of the destructive potential of the hurricane. So it depends on frequency, it depends on wind speed, and so forth. And the shading is the scatter among the 6 models. So we see in these kinds of analyses globally, that doesn't mean it's true everywhere, but in the global mean, we see rather substantial increases in this. And go back to the local, this is a point that Sonia made, which I cannot emphasize enough. Climate change is not a problem just for the future. It's already here. And I'm trying to get the insurance industry to understand that because they're basing decisions on actuarial data that goes back in some cases 50 years. It's just not accurate today. And I want to use this slide to illustrate that. This is a slide we did for the study for the city of Houston in Texas. And it shows, based upon very large sets of these synthetic tracks, the return period of storm total rainfall in excess of the amount you see on this axis. This is the rain produced by tropical cyclones over Harris County, which is the county in which Houston is located. And this is the return period. The return period is just the inverse of the annual probability. So if it's got a large return period, it's rare, okay? The blue is for the end of the 20th century. The red is a projection for the end of the 21st century. And the green is for the year 2017, which is when Hurricane Harvey occurred, whose rainfall total over Harris County is given by this blue line. All right, so the insurers are using a database of insurance that suggests that the return period of these storms is 2,000 years. By the end of the century, and that's pretty much what the models are showing as well. This was based on 6 climate models again. By the end of the century, we're down to 200 years, a factor of 10 increase in this kind of extreme event. But by 2017, we were already down to 800 years, 700, 800 years, all right? So the risk was 3 times larger than the insurance companies thought it was, and the city planners and everybody else. It's not a question just about the future. They're already wrong, okay, because they're basing decisions on old data that climate change has obviated. So very quickly, we can do the same kinds of things for these other sorts of storms. Here's a Mediterranean hurricane. Yes, there are hurricanes in the Mediterranean. They're a little different. They're rarer. They tend to occur in the transition seasons. This is one that's actually got a name called Zorba. Of course, with a name like that, it had to hit Greece, which it did. And when we run this similar kind of technique for that, we actually see that the change in the frequency of the storms is actually, they become fewer in the Mediterranean, but more in the far western Mediterranean and in the Black Sea. But the change in the probability of winds greater than 60 knots goes up everywhere because of projected climate change. Polar lows, getting a little bit closer to where we are now. Here's a beautiful infrared satellite picture of a polar low northwest of Norway, in between Norway and Greenland. And you can do the same kind of analysis. This is the track density of polar lows historically. From 2 different climate reanalyses. And then this is using the synthetic method, the change in the track density of polar lows going into the future. Basically an overall decrease, with the greatest decreases in the southern part of this region, but increases along the coast of Norway. So again, all climate change is local. So let me summarize. There's very compelling evidence that we're changing the climate in significant, risky ways. I think you all know that. I don't really have to repeat that. Among the many risks of climate change, and I've only obviously been talking about one of them, but extreme events are both early harbingers of climate change. You tend to see the extremes most readily, and among its worst consequences. Tropical cyclones are among the most damaging and lethal of these. $700 billion a year on average damage globally from tropical cyclones. So this basic theory says that the limit on the intensity of these storms is going up, which is why we're seeing storms of unprecedented intensity now in the historical record. Haiyan was the most intense tropical cyclone ever measured when it happened in 2013. 2 years later, that record was broken by Hurricane Patricia in the Eastern Pacific. Physics can be used to improve on climate models for phenomena like this, and also things like Medicanes and polar lows. And perhaps the most important point, global warming isn't just a problem for the future, it's a problem for now. Okay, thank you very much.
Thank you very much, Gary. As usual, very nice talk. And any questions? Eric, you want to? Yeah.
Thank you very much. I have a question on the technical question on this embedded model that you ran for the synthetic calculations. First of all, what kind of resolution do you need for that kind of model? And you also mentioned that it was a coupled system, so you also have an ocean model. And is that necessary for all of these types of storms, also the polar lows?
Yeah, both very excellent questions. So let's take the resolution first. There's not a straightforward answer. What we need is straightforward. We can run very specialized models and increase the resolution. And you numerically converge when your grid spacing is a few kilometers for the intense storms. The model has, as its radial coordinate isn't radius, it's absolute angular momentum. So the equations of the model have been recast with angular momentum as an independent variable. And so it has variable resolution. If you back transform, you see that in the eye wall, where you physically need the resolution, it's very high, and the stronger the storm, the higher it is. That's why it's not a clean answer. But it's also why the model has no intensity bias. Now, the coupling is really important. I mean, hurricanes are fascinating phenomena. They resonate with inertial waves in the ocean, and so you get very strong surface currents, which cause turbulence, which upwells cold water from deeper in the ocean. And it's a strong negative feedback on tropical cyclone intensity. And if you don't have that feedback, you're going to get it wrong. We know that from very detailed studies. And it means that the ocean, not just the surface, but the substructure of the ocean matters, including in the climate change problem.
Okay.
It's a very interesting topic. And I have a question, say, in your talk more on the changing of the intensity, and but sometimes, changing the tracks, also very important, especially for the extropical cyclones.
Yep.
Say, even for tropical cyclone, say, in southern part of China, we see now less frequent influence of tropical cyclone in southern China, especially in Guangdong, Hainan province. Mm-hmm. But we now see more and more in impact on the high latitude.
That's right.
Do you have any vision on this?
Yes, and it's something that's consistent both with the basic theory, which shows that the largest increases in this limit are not in the tropics, but in the subtropics, and with the downscaling. I mean, we actually did a study for the coast of China that showed decreases in tropical cyclone activity in the far south and increases in the east and north because of changing tracks and genesis locations. So it's not just about their intensity. It's not just about their translation speed. The tracks are really important. So that's why we say all climate change is local. You can't make a sweeping statement that there are going to be more hurricanes or fewer hurricanes. You have to look at the details. Yeah.
I take the chance to ask you the question, Kerry, about the when we talk about the changes of tracks and what I was thinking about was the current seasonal prediction model is already tried to catch this type of signal.
Yeah.
But the resolution is too bad. But do you see there is a chance to get some kind of signal which is useful for society as an early warning? And if yes, what kind of resolution we have to get to?
I do have a view on that there is a chance that for basin metrics over whole ocean basins, there is a chance. For predicting damage or any societal thing, there's almost no chance. And the reason that there's no chance is that from one year to the next, the sheer random nature of these storms, the stochastic variability, completely swamps. So even El Nino signals, which are strong, well-known, well-measured tropical cyclones, are swamped. I'll give you an anecdote that doesn't prove anything, but it's an illustration. Hurricane Andrew in 1992 was the most expensive hurricane up to that point that had ever hit the U.S. by far. It sank large numbers of insurance companies. It was one of the quietest hurricane seasons ever in the North Atlantic. Very few storms. If you made a seasonal prediction that were any good, you'd say very low probability. Can you imagine making wrong decisions? But that's an anecdote. If you look at the statistics, it comes out at you full force. So year-to-year chance rules. Yeah.
Thank you very much for this insight. And also, let's join, I invite you to join me to actually to thank all the three speakers for the fantastic talk they have given. Thank you. So that actually, and we conclude with our open session, public session for this workshop. Thank you for your coming also, all the participants.